equation with the same assumptions that we had made. Okay, the flow is homogeneous in x. So, that gives us the condition from continuity that there is no y direction velocity. Okay. After that we obtain that pressure is not changing in y and the flow is homogeneous in x. So, pressure is not changing in x also. So, from those conditions you can write down the x momentum equation and reduce it to this form. Okay. And then the boundary conditions are that at u y 0 this is u naught cos omega t and at u y tends to infinity it is 0 and the initial condition is also like this. Okay. So, as I was discussing towards the end of last lecture that this is very much like your this is very much like your spring mass damper system. Okay. Your spring mass damper system with an oscillating force. So, F naught let us say e to the power I omega t, the real part of this. If you have a force like this and you plot the displacement of this mass in time, you get some solution like this. Okay. You get a solution like this. Now, this has two parts to it. One is the steady state behavior, okay, and one is the transient behavior. The steady state is not steady state in the rigorous sense that it is not varying in time. The characteristics of that flow or of that solution are not varying in time. That is, this amplitude will be constant and the time period or frequency at steady state will be constant. There will not be any change or drift in these amplitudes or frequencies. Okay. That is why we call it a steady state. In nonlinear dynamics, we tend to call these kind of solutions as limit cycle solutions, although we are not doing nonlinear dynamics so far. Okay. And then the initial period is the transient period. So, we will also find two solutions to this equation. One is the transient solution and the other is the steady state solution. Okay. For the steady state solution, what we will say is, so first let us find the steady state solution. So, for steady state solution, we will immediately make the same assumption as we do here, that our velocity u as a function of y comma t is actually some capital U, or let us say let us write it as u hat y e to the power I omega t. Of course, it is going to be the real part of this. Okay. It is going to be the real part of u hat e to the power I omega t, just like you have here. You assume that x is real part of some capital X hat e to the power I omega t. Here I have introduced the y variation of amplitude. That is the only difference. Okay. The amplitude is allowed to vary in y. It is a PDE after all. It is not a single degree of freedom system. It is not an ODE. It is a PDE. So, the amplitude can change in y. The variation, the harmonic variation I am introducing in only time. Okay. Some of those of you who understand separation of variables by now can quickly see that I have separated the variables y and t essentially. Okay. I have separated those variables. So, at steady state we assume this to be the form of solution, and when I substitute it here, what I will get is that I omega u hat I omega by nu u hat equals d2 u hat over dy square. So, just by doing this kind of a separation, by introducing this harmonically varying component in the solution, I have converted my PDE to ODE. I have replaced the time derivative with I omega. Okay. You can quickly see that del by del t of u is I omega times u. Yeah.
Sir, when we are only interested in taking the real part of the expression, so why not just use the sine or cosine term, because essentially it will
You can do that. You can do the same variable. You can do the same analysis using those. You will get the same answer. I tend to use exponential because it makes algebra simpler. Okay. Whenever I see these sines and cosines, it is much more. It is easier for me to understand them in complex exponential. Whenever you have integrals like x cos ax dx, the standard trick of using the integration by parts twice and those kind of things, I tend to use exponential there and take the real and imaginary part later on. Okay, because integrating, differentiating, working with exponentials is complex exponentials is easier than sines and cosines for me. So you can definitely do that. You can assume, so you can assume something like, let's say u hat y cos omega t plus phi, something like this. Okay, you can do that and you can carry on with your analysis, you'll get the same thing. On. Okay, I have substituted this guy in the equation and I'll take the real part later on. Okay, so this is what we get for u hat. The solution of this, so for that first let me write I omega by nu as some eta square. Okay, and then the solution of this is u hat a e to the power eta y plus b e to the power minus eta y. Okay, what is the square root of I omega by nu? I omega by nu. I am already taking plus and minus values here, so I do not need to write plus minus there. Okay. So, this is basically 1 plus I square root omega by 2 nu. Okay. Square root of I is 1 plus I by root 2. So, I write eta as this, and when I write it like this here, u hat of y is a e to the power 1 plus I omega by 2 nu times y plus So, interestingly there is a real part and an imaginary part in the exponential. So, imaginary part is going to give us oscillatory behavior in y, but the real part is really going to decide if the amplitudes are going to explode in y or increase in y or decrease in y, right. So, the minute we have that equation, now we are going to convert our boundary conditions to u hat. So, if u y y equal to 0 t, so that means u hat y e to the power I omega t at t equal to 0, at y equal to 0 is u naught e to the power I capital omega t. Okay. Notice what I did here, I simply replaced u naught cos omega t by real part of u naught e to the power I omega t. It is understood that real part is on both the sides. So, I am just equating the full complex number. It is understood that the imaginary part of this complex number need not be equal. I am equating the full complex number because eventually I am only interested in the real part. Okay. So, I am writing this from which I get that u hat for y equal to 0 is u naught, the amplitude of velocity at y equal to 0 is u naught, and the other condition is that u hat y e to the power I omega t for y tends to infinity is 0. What does that mean? So, if you take the real part of this and see how can you impose y tends to infinity to be 0 is only when a is 0. Okay. If a is not 0, then your positive positive exponential will have some finite value which will blow up for y tends to infinity. Okay. So, this means a has to be 0. So, from here we get that u hat y is some b e to the power minus 1 plus I omega by 2 nu y, and for y equal to 0 it is supposed to be u naught. This means b is equal to u naught. Okay. So, u hat y is simply u naught e to the power minus 1 plus I omega by 2 nu y. What are the dimensions of this quantity? This quantity, let us say 2 nu by omega. What are the dimensions of this? Dimensions of kinematic viscosity are meter square per second. So, this is a length. So, I am going to write it like delta S. Okay. It is very similar to the penetration depth that we had seen in the impulsively moving plate, and usually this is called the Stokes layer thickness. This is called the Stokes layer thickness, and the idea is that approximately 2 nu by omega square root 2 nu by omega far away from the plate, the effect of the plate is maximum. Till that length, the effect of the plate is maximum. As you move, let us say you are 3 times this delta s or 5 times delta s or 100 times delta s away from the plate, the effect decreases. Okay. So, this gives us a characteristic length scale of the problem. Okay. Notice that throughout this problem there is no externally imposed length scale. Is there an externally imposed length scale? Is there an externally imposed length scale in this problem? What if I said, oh, this is meters per second, this is per second, so u naught by omega is an externally imposed length scale? What if I said that? Is u naught by omega an externally imposed length scale here? It is an externally imposed length scale. There is an externally imposed velocity and externally imposed time scale. Combining them, you can pose an externally imposed length scale. So, this is the intrinsic length scale of the flow. There is an externally imposed length scale of the flow on the flow as well. Okay. And you can compare these two. You can compare how is delta s compared, what is delta s compared to u naught by omega, and maybe towards later on in the course when we introduce asymptotics, we will see in the limits of this delta s being very small or very large compared to here, what does it even mean. For example, let us say the length scale imposed externally is u naught over omega. So, let us look at delta s over L. What is delta s over L? What do we get for delta s over L? So, it is omega over u naught square root 2 nu by omega, which is what? I can write this as omega times square root of 2 nu by omega u naught, or let us write it like square root of omega times square root of 2 nu by u naught. What are the dimensions of 2 nu by u naught? What are the dimensions of 2 nu by u naught? 2 nu by u naught. Huh? 2 nu by u naught. Nu is meters per second, meter square per second. And this is, okay, did I make a mistake here? Hold on. Yeah, you're right. This should be u naught square. Thanks. So, what are the dimensions of this nu by u naught square? Nu by u naught square is what? Time, right? So, this is like square root of omega times a time scale. Okay, this is like square root of omega times a time scale, that delta s by L is this. So, let us say when I say delta s by L is very small, let us say I say delta s by L is very small, that means this Stokes layer thickness is very small compared to u naught by omega. Physically what it tends to mean is that this frequency at which you are oscillating the plate, it is very slow compared to the time scale that you are imposing on the flow. Time scale meaning at what time scale is the effect of plate diffusing upwards. This is an unsteady problem. At what time scale is the effect of flow diffusing upwards? The frequency is very slow compared to that. And similarly, if delta s by L is relatively very large, okay, then you can understand it in terms of the time scales as well. So, what will happen when delta s is small compared to this u naught by omega, and delta s is large compared to this u naught by omega. So, this helps us actually separate out regimes of the flow. For example, I could have said that there is, let us say there is a plate oscillating over under water and there is a plate oscillating under glycerine. The effects you will expect the effects to be very different in both. The general characteristics of the flow will be same, governed by the same equations, the flow will be diffusing and all of those things, but you will expect the glycerin flow to be more diffusive, to look like it is more diffusive, it has a lot of lag compared to what is happening under water. Okay. So, those kind of regimes can be separated out by these kind of dimensionless ratios, the delta S by L. Okay. Those kind of regimes can be separated out by these ratios, and when we discuss non-dimensionalization, this is exactly what we will discuss. So, the standard dimensional analysis tricks that you are used to, forming pi groups and those kind of things, they are relevant to us in determining the length scales of the flow or time scales of the flow or velocity scales of the flow. Okay. Using those, we can actually separate out the regimes of the flow. Okay. I will show you how to do that, and most of this course after this discussion will be dependent on this regime separation. So, when we say flows are low Reynolds number, flows are high Reynolds number, what is Reynolds number, how does it appear in the governing equations, and how are you separating these regimes. Okay. This is what we will do.
In practice, does the no slip condition have limits?
Yes, that is a good question. In practice, the no slip condition does have limits in the sense of at what length scales are you operating. If you are operating at continuum length scales, there is no problem with no slip condition, but as you zoom in to micro or nano scales, then the no slip condition is not really true. Okay. You have to account for slip of the flow on these walls, because then the roughness of the walls comes into picture, and then you have to account for all of those geometrical things. In fact, it is not just about zooming inside, it is really about a dimensionless number known as the Knudsen number. Okay. Knudsen number is basically how rarefied your fluid is. Rarefaction means that, let us say there is an externally imposed length scale. Let us say this is the room that we are discussing. Let us say his question was, is there a limitation on imposing no slip wall boundary conditions in this room? I would say yes, it depends on the pressure of air inside this room. If I reduce the pressure so much that air is mostly, it is mostly vacuum inside, where there is very less pressure of air, in that case I would say that the air is rarefied inside the room. What it means is that the collisions of air molecules are happening very, very rarely. The mean free path length is almost comparable to the length scale of this room. In those cases, no slip does not work. Okay. So, either you zoom in to the level of mean free path or you make the mean free path larger. Okay. In both these cases, no slip does not work, but we will not do those kind of problems in this course. That is more of a gas dynamics, rarefied flows discussion. Okay. So, this is our solution u hat y this, and now I can write it more compactly as this u naught e to the power minus 1 plus I y by delta s, and so u of y comma t is simply real part of u naught e to the power minus 1 plus I y by delta s times e to the power I omega t. Okay. We can even separate these two, we can combine these two parts to have a more physical intuition of what is going on here, and that is how I am going to write it is e to the power minus y by delta s times e to the power I omega t minus y by delta s. What is this type of a solution? E to the power I omega t minus y by delta s. Where have you seen these kind of solutions? This resembles what? Wave propagation solutions, right? This is wave. This is a wave that is propagating in positive y. Okay. This is a wave that is propagating in positive y with an amplitude that is decaying exponentially in y. Okay. That is what this solution looks like. So, if you were to plot this solution at different times, you will see that there is a wave that is propagating in y. Okay. Sorry, this will look something like this. There is a wave that propagates in y, and as you go on this side, there is a wave that propagates in y with an exponentially decaying amplitude. Okay. Any questions so far? Any questions so far? So, this is what we have found for the steady state solution. Notice that we are, where did we make the assumption that we are looking at the steady state solution? The moment we assumed that the variation is harmonic in time. Okay, the moment we assumed that the variation is harmonic in time with a constant frequency and a constant amplitude at a given y, we impose that we are looking at a steady state solution. Now, in general, the solution of this equation will be, so let us say that is u s. So, the solution of this equation will be something like this, where this is your steady state and this is your transient solution. And the idea is that you are supposed to match the initial condition, sorry, you are supposed to match the initial condition using this transient solution. The intuition is something like this: the steady state solution will be, for all times, it will be a harmonically varying solution in time. The transient will be maximum at t equal to 0 and slowly it will decay in time and give way to steady state solution. Okay. The reason why we are looking at steady state and transient separately is because, again, for finding this solution I have assumed that it has a constant frequency. The transient does not have a constant frequency, the transient is not oscillating. Okay. As one of you remarked in last lecture, you said that we have to find the homogeneous solution first. This transient is that homogeneous solution, okay, as we will see in a minute. Why am I calling it a homogeneous solution? You will see that. So, what I am going to say is that this u, the total velocity, is this u steady state, that is u naught e to the power minus y by delta s y, y by delta s, and then this exponential e to the power I omega t minus y by delta s plus the u transient. Now, u of y for t equal to 0 has to be 0. This transient is also function of y comma t. This means this u of transient for y t equal to 0 has to be a u naught or minus of u naught e to the power minus y by delta s e to the power minus I y by delta s. So, in a way, this 0 boundary, this 0 initial condition I have converted into a non-zero initial condition for the transient, which is what you have. Okay. Technically, the transient is supposed to be not like this, but like this. So, that this plus this becomes 0, because that is what your initial condition is. Okay. This is what your u transient, this is what your u steady state will be. So, that is what I have done here. I am trying to find a transient so that I can match this initial condition. Let us get rid of this part. Now, what about the boundary conditions for this transient? U of y comma t is this u steady plus u transient, and then the boundary conditions on the velocity We have already matched with the steady solution actually. So, this now here you will see why am I calling this transient as the homogeneous solution. US at y, the steady state solution at y equal to 0 is equal to u naught e to the power I omega t or u naught cos omega t. So, these guys are equal. So, that means ut is 0, the boundary condition on transient solution is 0, because I have already satisfied the boundary condition for the steady state solution. So, in a way what is happening is that transient solution becomes a initial value problem with 0 0 or homogeneous boundary conditions. You have a initial value of u transient and that will decay with time. The steady state solution remains as is, you have an initial value of transient that decays in time, and their sum is such that we satisfy both the initial conditions and boundary conditions. Okay. So, u of t y equal to 0 is 0, similarly you will get u of t y tends to infinity is also 0. So, now the problem that we have to solve is this ut satisfies this initial condition and these boundary conditions, and of course, it satisfies this equation. So, del ut by del t equals nu del 2 ut over del y square is there with the given initial condition and boundary condition. So, this is your initial condition. Of course, there is a real part, I am ignoring that real part as of now. Okay. I am ignoring that real part as of now, and ut for y equal to 0 is 0, ut for y tends to infinity is also 0. How do we solve this kind of a problem? We have an initial value of ut and we are expecting it to satisfy these boundary conditions. How do we solve this problem? How can we solve this problem? How do we solve this problem? Huh? Why can't we use separation of variables? We can use separation of variables. We can use separation of variables, right? You can use separation of variables here, satisfy this initial and boundary conditions, and you will get an answer. Okay. So, I would leave that exercise to you guys. एक बार बोल सकते हैं?
Partial differential equation ut del ut by dt del t.
No, so u satisfies that equation, us satisfies that equation. The overall velocity satisfies that equation for sure, and I found the steady state solution by satisfying that equation. So, if the two parts satisfy this equation, then their linear combination will also satisfy the equation. Okay. So, you can use separation of variables here to solve the equation. One thing that you will have to be careful about is when you use separation of variables in this problem, since you have y equal to 0 and y tends to infinity, you will have to replace that summation over eigenvalues with an integral over eigenvalues. Okay. So, essentially there is another way you can solve this equation, and that is called using Fourier cosine transform. And Fourier cosine transforms are useful when you have semi infinite domains. Okay. When you have semi infinite domains, you can use these cosine transforms, and the idea is that your f x is basically f hat omega sine cos omega x, or let us write it as k dk, okay, from minus infinity to infinity, and f hat k is actually given as f of x cos k x dx with a 1 by 2 pi 0 to infinity. Okay. So, the idea of Fourier cosine transforms is you have a semi infinite domain, you have a function defined on semi infinite domain. So, what you do is you take an odd extension of the function for y less than 0, oh sorry, even extension of the function for y less than equal to 0. So, what you do is, so you have a function that is defined something like this. Okay. Actually, here you will have to use Fourier sine transforms, not cosine. I will just explain why. So, what you do is you have this kind of a function, and you do an extension of this function here, and then you apply basic Fourier transform. Okay. The sine transform is you have a function like this, and let us say you have a function like this, and you do an odd extension of the function and you apply Fourier transform. Okay. The reason why I have applied it like this for this function is because this function is 0 at 0. If I do a summation of a function which is this plus minus of this at 0, I will get 0, which is what we have here. For y equal to 0, the function, the velocity is 0. So, here actually you will have to use Fourier sine transforms, not cosine transforms. Okay. So, you what you can do is you have a velocity that exists for y greater than 0. Okay. I will extend the velocity for y less than 0 such that this is minus of for y less than 0. I will extend it, I will have an odd extension of velocity for y less than 0. Once you do that, you can apply the standard Fourier sine transform technique and find the solution of this equation. So, this is like an initial value problem with homogeneous boundary conditions on a semi infinite domain. Okay. These kind of problems you can solve like an initial value problem on infinite domain by extending the function to infinity. Okay. You had the function defined only on this side of the axis, you extended it down and then just use the Fourier transform. That is what essentially is going on here. Okay. You can look at the uploaded notes and the textbook for this. I think textbook does not have the details of this Fourier sine transform, but in the notes I have given that. So, you can take a look at that. Any questions so far? Any questions? You can also use separation of variables. Just go back and try applying separation of variables here as well. You can do that. You will have to be careful about the eigenvalues here. Okay. For example, when we write separation of variables, when we get those sines or cosines and we say these are the possible values of that lambda. Okay. When you have boundary conditions, when you have a bounded domain, here you do not have a bounded domain. So, what you will get is there is an exponential minus y, and that satisfies the boundary conditions for any lambda. It does not have to be that discrete lambda values for which your boundary conditions will be satisfied. It will be any values of lambda for which boundary conditions can be satisfied. So, in that case you do not do a summation, you do an integration over all possible values of lambda, something very similar to what I have done in notes for flow due to rotating cylinder. Okay. Flow due to impulsively rotating cylinder, just go through the working of that. I have solved that using separation of variables only, and there we obtain this fact that the general solution satisfies the boundary condition at y tends to infinity or whatever variable is tends to infinity for all values of this lambda. When you do the separation of variable, you will write this you will do dx by dt equals this d2y by dy square equals some lambda square or something, right. For all possible values of lambda, the boundary conditions are satisfied. So, in that case you have to integrate over all possible values of lambda. Okay. All real values of lambda, possible, all real values are possible values actually in that case. Okay. So, with this I will close the discussion on different solutions of Navier-Stokes equations that we can find under very restricted assumptions that we have been making. For example, you cannot have a truly infinite plate, okay. You will have to have edge of a plate somewhere. So, when you have that, you cannot anymore close to these edges, you cannot anymore assume that the flow is uniform in x. Close to the edges, you cannot assume that the flow is uniform in x. Okay. So, under these kind of assumptions, we can solve Navier-Stokes equations. Whenever we form a linear equation out of them, notice that in all of our examples, the nonlinear terms were very conveniently dropping out. Okay. Nonlinear terms were very conveniently dropping out of our governing equations. Okay. So, that is why I could solve these problems, but when you have these nonlinear terms appearing in the equations, then things become more complicated.
There are no exact solutions with nonlinear terms.
No. There is no, I mean, people claim that they have found some or at least proved the existence of Navier-Stokes solution for in a general setting, but I am too dumb to go through that 15 pages of dense mathematics. Maybe one of you can go through that, but yeah, it's I mean, if after 15 pages you can just prove there is existence of solution, then imagine finding the solution. Okay. So, this problem of Stokes oscillating plate, or actually a lot of other problems also, but I just choose this problem usually. This gives us a nice segue into our next discussion, and that discussion is on dimensional analysis. Now, most of you have probably seen dimensional analysis in your previous fluid mechanics courses, where you were looking at, okay, form pi groups out of these variables. Okay, someone gives you, okay, the velocity of this pump and the flow velocity depends on these parameters of the pump, and then find the pi groups and so on and so forth. Okay. Now, whenever you form those kind of pi groups or the non dimensional numbers, they are not basically saying that velocity is just a function of those variables. No, velocity will be a function in a flow which is not uniform. Velocity will be a function of x, y, z and t. Okay, those are the parameters of the flow that you are using. They are not really functions of omega and things like that. I mean, they are parameters which you can change. Okay, and the idea is, when you form those pi groups, you were actually determining the characteristic scales of the flow. Okay, whenever you formed those pi groups, you were actually determining the characteristic scales of the flow, and that brings us to this dimensional analysis, that okay, once you have found the characteristic scales of the flow, what do you do with those? Okay, what do you do with those? For example, you may recall some problems like this, that let us say you have, I don't know, let us try to cook up a problem which looks very similar to your previous dimensional analysis problems. So, let us say you have a flow that is happening. So, you have a flow that is happening due to gravity. So, you are ignoring, let us say, a very simple problem. This is a beaker or a tank, and a flow is coming out of this orifice, and the area here is some a, and then you were just given, okay, or the diameter is d, you were given that the, okay, the exit velocity is a function of the diameter, gravity and this height and blah blah blah. Okay, and then you were said okay non-dimensionalize and find the pi groups. What you are essentially doing by finding those pi groups is basically you will say okay root gh or u by root gh is that pi group here. Okay, what you were essentially doing by forming this u by root gh is you were determining what is the characteristic velocity scale in the problem. You were not solving for the actual flow. Okay. Notice in all of those problems, if you go back and look at those long statements, you will see that it was never said that the velocity of the flow everywhere is a function of these parameters. They were always saying, okay, exit velocity at the orifice is a function of these parameters. And now you know better, exit velocity also needs to be pointed at a particular location and said that it is a function of these parameters. So, whenever you were doing that, you were actually finding the relevant scales of the problem, the characteristic scales of the problem. And what do characteristic scales actually mean? It is, as we have discussed, what kind of a ruler you will bring to measure that flow. Okay. For example, in the Stokes oscillating plate, let us say this delta S comes out to be 1 millimeter. Will you bring a meter scale for that or a vernier caliper for that? Okay. That gives you an intuition what kind of scales or rulers you will bring to measure the flow. Let us say the velocity at of the plate is 1 meters per second and you bring a probe which has a least count of 5 meters per second. It is useless. These relevant scales or characteristic scales give us an intuition of what kind of values are we expecting. Someone comes to you and says, oh, my plate was oscillating at 1 meters per second and at this height I measured the velocity to be 100 meters per second. You will be like, shut up. Okay, that makes no sense because your plate was oscillating 1 meters per second, the characteristic velocity scale is 1 or 10 meters per second, it can't be 2 orders of magnitude higher 100 meters per second here. Okay. So, it gives you an intuition of what kind of values to expect in your flow. These characteristic scales give you an intuition of what kind of values to expect in a flow. Now, usually all the flows that you see in reality, they will not have a single characteristic scale. It will depend on what kind of quantities you are interested in measuring. Okay. For example, even by just by the action of speaking, I am creating some flow inside this room. Okay. So, there is maybe a length scale comparable to the length scale of my mouth, you can formulate, oh, this is the length scale of the flow that is inside this room. But if someone comes to you and says, okay, how much is the pressure increase in the room because of this guy speaking, you would say negligible, there is no pressure increase. So, it depends on the practical quantity that you are interested in, which helps you determine what is the relevant scale of the problem. Okay. And so, all of these times you were you were deriving some relevant scale of the problems. These are also not all relevant scales of the problems. Okay. So, what do we do with these relevant scales? What we do with these relevant scales are define dimensionless variables. Okay. We define dimensionless variables, that is what we say is okay, let us say you have velocity which is a function of space and time, okay, and let us say you have a velocity scale which is equal to u naught in all three directions. Using this, what you define is a dimensionless velocity which I am going to denote by a u star. Okay. And the notation that I am going to use for scales is something like this. So, these square brackets denote that I am talking about the characteristic scales of the variable. Okay. So, similarly, let us say the characteristic length scale is L in all directions, the characteristic, yeah, that is it, the characteristic pressure scale is some P naught in the flow. Using these, I can define dimensionless coordinates and dimensionless pressure. I can also define a dimensionless time, and I can make a dimensionless time using a time scale using u naught and L. Okay. I can write that it is equal to u naught T over L. And now let us try to do the non-dimensionalization of equations or try to derive the dimensionless governing equations. So, we know that okay, for this course we are mostly looking at incompressible flows. So, this is our continuity equation. Okay. Since you have non-dimensionalized the coordinate also, so this is basically del star dot u hat star u star times a u naught over L equals 0, where this del star I am defining as 1 by L or sorry L times the gradient operator. Okay. So, basically I am non-dimensionalizing everything. Okay. I am eliminating any dimensions from anywhere. Okay. This del star dot u star. So, del dot u has a dimension of what? Del dot u has a dimension of what? Del dot u has a dimension of what? Per second. Del star dot u star has no dimensions. Okay. Del star dot u star has no dimensions to it. So, I am converting all the terms dimensionless. Okay. Why I am doing this? It will become clear to you in a minute. So, let us do the same procedure for our Navier-Stokes equation, the momentum equation. एक बार फिर से बोल सकते हैं उनको, दिस इज नॉट ओके. So, what I am going to do is I am going to non-dimensionalize here each term. So, this is basically u naught over. So, there is a dimensionless time that I have defined L by u naught. So, this will be u naught square over L del u star over del t star plus a u naught square over L u dot del u equals minus p naught over rho L del star p star plus nu u naught over L square del star square u star. Let us divide this equation by u naught square by L. So, on the left hand side I will get this is u star dot equals minus p naught over rho u naught square plus nu over, so nu L no nu over u naught L del star square u star. This is what I get when I non-dimensionalize my momentum equation. What are the dimensions of this p naught over rho u naught square? What are the dimensions of this p naught over rho u naught square? Dimensionless, right? This is a dimensionless number which is usually called the Euler number denoted by EU. And what are the dimensions of this? So, nu by u naught L we know is basically mu by rho u naught L and this is very familiar. This is called 1 by Re, where this is Reynolds number. And this is Euler number. So, what we just did by writing writing this dimensionless form of equations is we found out what were those pi groups that you were finding in these. So, on the left hand side you will find something like this, on the right hand side you will write it as a function, some other function of another pi group, right. In the standard dimensional analysis you have done that. What we have found those pi groups, what we have done is found those pi groups naturally from the governing equations. Okay. From non-dimensionalizing the governing equations, we have found those pi groups. What do these pi groups or what do these dimensionless numbers, what do they encapsulate? Okay. So, for example, this Reynolds number, you guys have probably seen these kind of definitions. What does this Reynolds number encapsulate? What is this a ratio of? Inertial to viscous forces. So, you know these kind of ratios. So, you will write this as u naught square, let us say L square and then mu u naught times L. So, this is pressure times area, this is viscous stress times area, sorry, this is viscous stress times area. So, you will say, oh, this is some kind of pressure force or dynamic or inertial force and this is some kind of viscous force. I can also look at it as ratio of time scales, by the way. I can look at it as ratio of time scale. So, this is what u naught L over nu. What is nu? This is meter square per second. So, what I can do is if I divide this by L square and this by L square, what do I get here? The numerator is u naught over L and the denominator is nu over L square. Nu over L square has dimensions of what? 1 by time. So, this is essentially a viscous time scale over an inertial time scale, u naught over L is 1 by time. So, what does a large Reynolds number mean? In terms of forces, you guys will say, oh, large Reynolds number means that the inertial forces are very high compared to viscous forces, whatever that means. Okay. In terms of time scales, you can say that a large Reynolds number means that the inertial times are very small or very fast compared to the viscous times. Okay. You can also visualize this in terms of length scales. So, it is not necessary to visualize Reynolds number only as a ratio of forces always. You can choose the visualization based on the kind of problem you are dealing with. If it is too difficult to visualize forces, but it is easier to visualize time scales, then visualize it as time scales. Okay. This Euler number, this is basically telling you what is the pressure scale in the flow compared to this rho u naught square. Okay. Let us say I give you an example of a flow where flow is mostly viscous, flow is highly viscous, the pressure you will assume to be balancing viscous stresses. Okay. You will assume that the pressure is generated in the flow due to viscous stresses. In that case, pressure scale is not always going to be rho u naught square. Okay. As we will see in a couple of lectures when we look at low Reynolds number flows, pressure scale is not necessarily always rho u naught square. There is another pressure scale possible which you can see from here, and that is, let us say, mu u naught by L. This also has Newton per meter square dimensions. Okay. This is also stress, right, mu u naught by L has dimensions of stress. Okay. So, mu u naught by L can also be a scale for pressure. And Euler number, what it is doing is it is comparing, okay, how does your pressure compare to this quantity rho u naught square? It need not always be 1 or close to 1. Okay. So, in our next class we will discuss how to use these dimensionless numbers to further reduce our equations.